All right, so moving on to the next basic concept of chemical equilibrium. Now, we must have already understood what chemical equilibrium is. So this video is not a basic, like from base level understanding of chemical equilibrium. This video is intended just to like recapitulate important informations, important concepts like the law of mass action. So what does the law of mass action say? That at equilibrium, so let's take an example of a reaction which can be represented, very basic representation. Say you have more reactants in here. This is giving you products like something like this. Okay, so what does the law of mass action say? The law of mass action says that if this reaction is in equilibrium, then the ratio of, and I'll comment upon the notations, like what does exactly the square brackets represent. I'll just comment on that. At equilibrium, this ratio, and this goes on, like you understand what this means. Like if you just go on like this, whatever the numbers are, you just, whatever the values are, you just put it there. At equilibrium, this quantity is a constant. So this is the law of mass action. Now what does this thing mean? And I'm just representing I just as a common element I. This means the activity of I, right? This does not mean the concentration of I. So in the law of mass action, or in previous like in preliminary classes when we discuss the law of mass action, we generally try and say that the thing that is inside the bracket is basically concentration. Now, the law of mass action, if we say that the thing in bracket is concentration, that can only be true when the concentrations are extremely low. Why? Because when you have higher concentrations in the solution or in anywhere, so when you have higher concentrations, then there are interactions between different ions or different atoms in that solution. So let's assume that you have Fe2 plus in the solution, right? And there is so much Fe2 plus in the solution that one of the other Fe2 pluses is interacting with this Fe2 plus, right? So since they are charges, there will be some kind of electrostatic forces acting between these two. Now, law of mass action does not assumes that there is no interaction between these different kinds of species, and there can be multiple species, not just Fe2 plus. The ions will be more problematic because of their charges in them. There can be cations, anions, and other different things. But even normal atoms with no charges can become problematic in that sense, because if you have more concentrations, they become closer, the different atoms come closer and they start interacting with each other. In law of mass action, we say that there is no interaction. So when is there no interaction? When they're very, very far apart. That is the only case in which we can say that, okay, there is no interaction, right? Because if they're interacting, that means there are some other forces that are getting involved. And if there are some other forces, then they have to be taken care of, right? So if the solution is extremely dilute, then the concentration is basically true. Then that is fine. Okay, if the concentration is really small, you can use concentration values in here. But if the concentrations are even slightly even if it is like 0.1 molar or something like that, it might not be valid, right? And that is why we come up with this idea of activity of I. Whatever is in here, that means this is activity of the species U, V, A and B, whatever, right? And these are the stoichiometric coefficients, you know that. So activity is basically the concept that comes in to explain the law of mass action. We need this. Why? Because this gives you the idea of the effective concentration. It is not concentration, it's effective concentration, because not everything will be taking part in this. So there is a modified amount of concentration that can only be a part of the action, and that is probably, it's a very weird way of saying, but it's true. I mean, there is only a small part of the whole thing that is present is actually doing the actual work, if you put it that way, right? So we do not use concentration, we use activity, right? So activity is being used, and whenever you have gas, so for analogous things, you cannot have like partial pressures. Like if the partial pressures are really small, what if this is a gaseous systems and everything that is involved here is in terms of pressure, we'll also see that. But when you have pressures involved, if the pressure is very less, then yes, okay, you can use pressure. Analogous to this, when you have the concentrations are very small, you can use concentrations. But when concentrations are not extremely small, not as close to dilute, then you have to use the concept, then you have to use the activity of that, right? And we will understand how to calculate activity later in the class, but for now, understand activity as the effective concentration of the species. If you get it to the gaseous state, the effective partial pressure is called fugacity. So it's analogous concept. Concentration, partial pressure, activity, fugacity. Okay, so there's effective partial pressure, fugacity. Okay, now when you do this, when you get all the activities, we saw that at equilibrium, we get a particular, if this thing is at equilibrium, at a fixed temperature, this ratio will be fixed. When you change the temperature, this changes. So this is a way of writing that, okay, whatever that ratio is, we'll call that chemical equilibrium, like K. So that quantity, the constant of equilibrium, is a function of temperature. I mean, if you change the temperature, things will change, of course, right? If you change the temperature, things will change. But for at a fixed temperature, if you fix the temperature, then if the system is at equilibrium, the ratios will not change. Now, if it changes, then we'll see what happens. This system resists changes. This system becomes like an organism of its own, right? So this behaves like a live organism. Like if you change certain things, it will try and resist those changes. So we'll understand that. Okay. So now, if this thing is, all thing is in solution, we generally call it Kc or K equilibrium, things like that. So whenever you see the K, you get the idea that we are talking about the equilibrium constants, right? Now, what if this whole system is in the gaseous phase? Now, in here, we saw that, okay, whatever the concentrations were, we are taking it as a solution, keeping in mind that these were all kind of like solutions. What if this whole system was gas, like everything was in the gaseous state? Now, for an ideal gas, we know this equation, PV is equal to nRT, right? So the pressure of any individual is something like this, right? I representing the ith component, right? So in here, so for this system, how do we calculate the activity or the fugacity? How do we calculate that? So basically, how did we calculate the concentration of anything? Concentration is basically the number of moles by the volume, right? So this is basically the concentrations. What is Ni by V? How can we write Ni by V? If you rearrange this, you see Ni by V becomes Pi by RT, right? So everywhere in which we had N of I, basically, we'll have to get P of U by RT, P of V by RT, P of A by RT, and things like that, okay? So in here, this whole equation then becomes P of U over RT to the power of U times P of V over RT. So this is signifying the element or the component V, not the volume, okay, over small v and so on, over P of A over RT, P of B over RT B, and so forth. So this whole thing can now be rearranged as the P of U over U, P of U times P of V, V, P of A, P of B, B times, so I'm writing it down here, 1 over RT, you'll get the summation of all these, U plus V plus dot 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 dot. So basically, the sum of the stoichiometric coefficients of the gases that are there, of the products, minus A plus B plus, so this is the summation of all the moles of the gases in the reactant side. So basically, this term is represented as a delta N. So what is delta N? Delta N is the summation of all the number of moles of gases in the product side minus the summation of all the number of gases in the reactant side, right? This becomes delta N. So what this becomes then is, this was Kc, right? So this was Kc. This was K. Now this whole term is written in terms of pressure, so I write it Kp, and then I have 1 over RT over delta N, right? If you rearrange this, what this becomes is Kc times RT to the power delta N becomes Kp. This is an important reaction, important equation that connects the Kp and the Kc of any reaction. Okay, so now we know how the Kp is represented. Now we also know how the Kc is represented, and if the gases behave as ideal gases, this is the equation how you can do, right? This is just the revisions of some previous concepts.